Bună seara, Cluj. Hello. Thank you first, Vlad and Ioana and Camelia for inviting me here and for putting together this very, very nice event. And I also, before I move on to my talk, I'd like your help for a minute. I'm actually dedicating my talk to two people who I owe a lot in my life. As you can imagine, I stand here because of people in the past, mentors, that believed in me and encouraged me and saw the value in me when I needed it most. And so my professor, Constantin Cosma, from University Babeș-Bolyai, where I graduated with my bachelor degrees in physics. He unfortunately passed away in April, and I'm really grateful to him and his wife, Doamna Felicia Cosma. I hope she's here. Thank you. And my father, who passed away 6 months ago, and again, who's been a tremendous resource for me in my life. So, back to innovation, Silicon Valley. I don't know if anybody else showed the map of Silicon Valley, but you can see the number of companies and the density of it. And here we are, NASA Ames Research Center. That's where I'm coming from. And I work there in an organization called the Space Portal, Portalul Spațial. And here are a couple of the startups and the partners in the private arm of space exploration that we usually work with on a custom basis. Virgin Galactic, Made in Space. They put a 3D printer on the International Space Station. NanoRacks, they're commercial providers for opportunities, both in the satellites as well as in the microgravity research, and I'll explain what that is. Spire actually is a spin-off from NASA Ames Research Center from one of the student programs we had 2 years ago. They're now in Series C of fundraising. They're doing amazingly well. And these are my colleagues. So we're NASA's think tank. We're the innovative arm of NASA, and we always look forward and think forward. And as you can see, I think Tim Draper said yesterday that an efficient number for a team is 5. We've exceeded that, but we're still handling it pretty well. So I'm really grateful to be part of this amazing team. And this is our network. And our network ties to the ecosystem that we're trying to build. And the ecosystem, as any part of an economical ecosystem, has at least three components: supply, capital, and demand. And we, as the government, we sit in the middle of it, and we operate on a daily basis at the intersection of these three components. And we have a couple of we have partners all over the triangle, the ecosystem. Primarily, we're right now focused in building the demand. And I will try to talk to you, and I hope you can follow me, from the perspective of creating an economy in Earth's orbit. And so let's go back to the notion of economy and where we are in democratizing space these days. Surprisingly, probably, to you, we actually have the equivalent of Wall Street for space. It's called New Space Global. And they're following the market, the new markets that are emerging for new space, from the existing one, where spacecraft and launch vehicle providers are dominating, and that is really a reflection of the $2.5+ billion invested in 2015, and that's really a number that has increased between 2005 onwards. And at the same time, they're also looking. So if you look at this chart. I think I'm running out of battery, so I can point with my finger maybe. So as you go on the chart from left to right, you're really looking at verticals in this emerging new market of space, the existing ones that are more solid and established towards the potential ones, human spaceflight, microgravity research, in-space services, space resources, and space-based energy. And I would actually put space-based energy earlier because of a couple of considerations. So let's try to understand this again from the perspective of a terrestrial economy. What is the definition of an economy? It's very simple. You have resources, and then you put it through a process, and then you create a GDP or you create value at the other end. That's in a very simple connection. And this map in particular, it comes from Khosla, Global Foundry, and CIA. You can find it on the CIA Factbook website. Sorry. It's not a direct reflection of the resources, but it is the map of the global export. And you can really see which countries export what exactly. So you have Russia, for example, with a lot of petroleum and petroleum products and oil, US with capital goods. In Europe, you have a lot of mechanical equipment, etc. But it is a reflection, again, of the resources that that country has, because whatever you have in excess, you're going to export and you're going to import whatever you need. So that's the basis of economy. The other thing that's really interesting, this is a new book that came out. It's called Connectography, and it's trying to map the future of global civilization. And as some previous speakers before have talked about, is we're really seeing a move towards globalization, as well as we also see a need for resources, and we're challenged in how do we deal with a growing population, a moving population because of pretty much open borders, and with not many new resources that are available. So one of the interesting things that I found in particular about this chart is that the world economy is not structured anymore around the 196, 97 countries that exist in it. By contrary, what this map is showing, and this is really, the circles are the GDP, which is right now a reference economic measure of wealth. The GDP that is generated in different spots around the world, and that's in trillions of dollars. And the conclusion from this is that the world economy is really structured around mega cities. So the globalization process now is sort of balancing out the powers of government. What does that mean? That's a really interesting question to ask. And what does it mean also in terms of going back to one type of resources? Let's look at raw elements that underlie industries. Industries of which products we carry in our pocket and we calibrate our lives around. Just a couple of examples. Let's talk about nickel, copper, zinc, platinum, lithium, tungsten, and titanium. Apparently the conversion missed that line. So these are raw elements that are non-replaceable, non-renewable, which means once we exhaust the resources, there's no other source for it. And we know approximately the global reserves, and we also know the demand. And we can estimate, based on a constant demand or on an exponential increase of the demand, when are we going to run out of these raw elements. And those that are highlighted in red, and again, this is just a snapshot of a longer list, those that are highlighted in red, we're going to run out of them by 2050. Now, that's in your lifetime, in my lifetime too, but, next generation. So let's move now from a couple of these elements in the perspective into two very entrepreneurial efforts out there. Two companies. This one, Planetary Resources, and the whole idea of Planetary Resources is to try to capture asteroids and mine asteroids. And asteroids, we map them pretty much in our neighborhood, the asteroids that are in our neighborhood. And when I say neighborhood, think of space, space outside of Earth. So we map these asteroids, and they're of different kinds. Some of them have a lot of ice, so that's a source for water. Some of them are more carbonaceous. They have carbon in them, a lot of carbon or carbon-based materials, and some of them carry a lot of metals. These companies are really actively working in trying to line up the technologies and get a good example out there in terms of supplying resources for raw elements. Next one is called the other, I could say a little bit competitor on the market, in the same market, Deep Space Industries. They recently secured an investment from the Luxembourg government, so they're now working very closely with the Luxembourg government, although their company headquarters is in the NASA Research Park, where I sit too. And their idea is, again, to capture asteroids as well as process whatever they're able to mine on that asteroid and then send products back. So the capturing technology exists. We haven't really used it in a real-life example, as well as the way to process the ore and extract the raw mineral, which is what they call a microgravity foundry. And maybe before I really reach my chart about microgravity. Microgravity is the same as reduced gravity. The moment you leave Earth's gravitational field, out there in the Earth-lunar space, which we call cislunar space, you have 6 order of magnitude reduced in one of the fundamental forces that drives life on planet Earth as we know it. So everything that needs to be processed or executed or run in a reduced gravity environment needs to be redesigned from scratch, basically, in order to work. And we do a lot of testing of these technologies to a lot of different NASA programs, such as Flight Opportunities, Game-Changing Technologies, NASA Innovation, Challenges, etc. So these technologies then become available to be transferred to technology transfer to some of these companies, and then the companies then are going to commercialize them. So, so between Earth and asteroids, which is far to the right, let's see what happens at the edge of space, closer to home, which let's think about Earth's orbit, either low Earth orbit or geostationary orbit. In particular, I'll talk about low Earth orbit. And how would we think in terms of defining, creating, and stabilizing an orbital economy beyond satellites, which is right now the opening door, the sector that's grown a lot. So, and why are we talking about this? What motivates now? What's the game changer? Up to 2010, the government used to own and operate every single capability of reaching space, whether we talk about parabolic flights through the NASA KC-135, which, by the way, is called the vomit comet because almost everybody who flies on it has experienced that secondary effect of microgravity. And then you have suborbital, so that's reaching real higher up, or orbital, the space shuttle. Between 2010 and 2015, so roughly where we are today, we've seen an explosion in terms of private capability that now secure launch system, launching things into space, operating things into space. So we're shifting now from a government-owned and operated paradigm to commercial operated and to commercial providers. What that means is, and our reference measure internally to the space geeks is price per kilogram or pound to LEO has come down from, let's say, 30,000, that's ballpark, to about $5,000. And the projection, again, looking at the total investment that come from space, from the private investment, we're projecting that this investment will go up. So that was a really big barrier for business. Nobody wants to buy products or to pay a transportation system that's prohibitively expensive. Nobody wants to operate on that. It's really counterproductive in terms of the infrastructure that supports an economy. Not only that, but the frequency of flights, or how fast or how often you can access any of these three regimes, was also maybe once or twice a year, and now we see 3 to 6 times a year, and it's really accelerating, moving to monthly flights. So here's the infrastructure. It is important, and we see this in Romania. I mean, after so many years, we still don't have highways crossing this country, and I think that is detrimental to the economic growth of Romania, my outside perspective. So probably we're going to have a better infrastructure to go into low Earth orbit than Romania is going to have to support its economy for the next decade. And that's unfortunate, and I don't think, I don't think the prices are comparable. Anyhow, so right now, what we have in space on low Earth orbit is the International Space Station. And it's been inhabited permanently since 2011. What I'm showing here is the current capabilities. I'm talking about the Dragon capsule, SpaceX, Elon Musk company, as well as Cygnus. The Dragon capsule has the ability to return to Earth. Cygnus is normally taking cargo, so these are both cargo carriers to the International Space Station. They're taking cargo to the International Space Station. Cygnus normally is loaded with garbage, and then it burns upon re-entry. So that's the way they are able to remove trash from the International Space Station. What we're looking at beyond this is the growth, again, of the suborbital regime, and there's several companies that are working in providing capabilities there, starting with Blue Origin, Jeff Bezos' Blue Origin. And you also have a lot of these companies working in providing crewed transportation, which means taking humans to the International Space Station. Right now, the only capability is owned by the Russians, and it's the Soyuz capsule. Beyond that, we're really looking into working into creating successful examples for free flyers, automated, teleoperated facilities, as well as orbital manufacturing, space manufacturing. And many of these also rely on the ability of creating sample returns. We do have these technologies, and we're working in trying to close the business case for it. So let's go back, recap, orbital economy, okay? We said before that an economy takes resources and turns them into products or goods to spur an economy. So from the perspective of globalization, so we do have, sorry, I'm going to start from bottom up. We have space resources. I can think of a few, like the vacuum of space. There's free-floating atomic oxygen. It's been actually used for molecular beam epitaxy. Cold of space, solar power, direct access to solar power. It's basically infinite solar power. These are a couple of really cool resources that we have in space, and we can turn them into real goods for an economy. What we also need, again, from the perspective of globalization, the question comes up of who do we want to be as humanity when we go to space? Right now, the outer space law says that whatever is launched into space belongs to the country from which the launch has happened. So if US launches a satellite, that satellite is owned by the US. If Russia launches a satellite, that satellite is owned by Russia. And so it makes, for example, cleaning orbital debris or recycling orbital debris very difficult, which again, it becomes a real problem right now. So do we want to create like a global entity? Do we want to work with the United Nations? Who's going to take charge of this? These are really actual questions that we're asking, and we're working with a couple of organizations to at least initiate a dialogue. We're talking about creating an Internet of Space, meaning beyond what's beyond the cloud, what's beyond the Internet of Things, and again, a global connectivity mapped onto Earth. What does that entail? And again, I think Vlad invited me here to try to help you explore opportunities for this amazing entrepreneurial community here in Cluj in terms of what you can do and how you can participate or contribute to these challenges and opportunities. We also need laws and regulation. Imagine that in the next 10 years, we would allow companies to incorporate in low Earth orbit. Why incorporate on Earth? Let's incorporate in space, and let's operate companies in space. We need to encourage that. We need to create, again, the legal and regulatory mechanism to allow that. And once we have this activity in low Earth orbit, like any economy, we're going to need a currency. So one of the activities that I'm actually exploring right now is with the electric chain. And the electric chain is actually, in my opinion, a better version of Bitcoin. So it's still an electronic currency. It's a blockchain type of currency. But what it does is it has a real resource at the other end, which means it's solar power. So this electric chain connected many solar powers around the globe, and they're using blockchain technology and mining to create solar coins. So I think that would be a great example once we put solar power, space solar power, up in orbit to then create the basis for solar currency. In fact, I met the other day someone from England who created the first orbital bank. They want to be the first bank that operates in orbit. So we need these currencies for not only for intra-orbital transactions, but for Earth-to-orbit transactions. There's another company out there that is actively working with a lot of satellite providers to put orbital data centers in space. And that's not only for cooling, but also for processing a lot of the data that right now is acquired in space through either remote sensing or hyperspectral imaging. So these kind of needs are actually met in space. And the other case for data centers, they're about 30 or 40% of the needs to operate a data center on Earth, the energetic needs, are because of cooling. And so you have natural cooling in space. And also you wouldn't need water for cooling, which gets polluted or in the process of cooling a data center. So let me talk a little bit about microgravity, because this moves more into the space manufacturing aspects. Why would we want to manufacture things in space? The reason for that is most products have better quality in space than on ground. A lot of materials, when we make them on Earth, they're a mix of elements. And so elements have different weights. And some of them, you will see a lot of segregation. In space, you're able to keep a uniform distribution of these elements, and so the materials that you're able to build from them have much better uniform properties, and they have reduced effects. A lot of the poor performance of the materials that we operate on Earth directly tie to the existence of defects at atomic scale in these materials. Gravity impacts, actually, so you also have no wall contact, because you have droplets as well as spherical forms in space. And so that's, again, exploited for many different purposes. That's more on the material side. On the life science side, there's crystal growth in space, and usually there's about 20% chance that the crystals that you grow in space have higher resolution than on Earth, which means you can characterize them better, and you can apply them to design better drugs and to grow better semiconductor crystals. Bacteria, for example, in space, they sense the lack of convective currents, and because the existence of convective currents on ground acts as a stressor for these bacteria, when it's removed, bacteria grow much faster and they become much more resilient. At cellular level, we also see that a lot of cells, when you look at the genetic profilings of these living cells, they turn on ancient genes that are responsible for adaptation, and you see a very big difference between upregulated and downregulated genes compared on ground and in space. So gravity underlies every single phase diagram, and maybe call me like I'm a scientist. So I think in terms of phase diagrams, whatever is around us has a phase diagram, and we do not normally think as gravity being another axis that's important to these diagrams, and we started to explore this in space. So humanity has a database of information about these phase diagrams on Earth, and now we have a second data point that we started to explore in microgravity. But this will be a huge driver to innovation. How can we return this microgravity value, the value of microgravity to Earth? So it's three ways. New insights. You can identify new end states of systems that otherwise are inaccessible on ground, and by knowing that there's a new state, you understand new physics, you understand new mechanism. You can reprocess things in space. So here's an exotic optical fibers pulled under gravity conditions, and the same the same fiber pulled in microgravity. So you can visually see at this level the transparency, which means you have less defects, which means you have less attenuation properties, which means you could, with one of these fiber, you could have a cable between the US and Europe without repeaters. That would be transforming to the telecommunication industry. And then we could manufacture in space. As I said, we already put a 3D printer in space, and because, again, we're a technology conference here, we have the technologies to actually, we have these things that are called gecko grippers. So you throw them out, they attach to an object, they are able to detumble it and bring it back to you. And once you bring it to you, you could do some form of a laser ablation to separate the elements, and then you can use them as feedstock for a 3D printer. And we've done the physics, first order physics analysis on that, and that's doable with the solar power that could be generated, again, in space. So it's self-sustainable. And because we're talking about big problems on Earth, here's one example. Every single one is guilty of this one. We carry an integrated circuit in each of our pockets, right? Our cell phones, they have integrated circuits. To make an integrated circuit on ground right now, because we're in the nanometer scale regime, we use about 2,200 gallons of water, multiplied by 4, 8,800 liters of water, and roughly. That's the average amount of water that's used to cool one integrated circuit. The production of integrated circuits in 2015 was 900 billion units. That's huge. None of that water is returned in its pristine form back, and actually the industry pays billions of dollars for environmental violations. Okay, in '95, NASA deployed behind the space shuttle what we call the Wake Shield facility. That's a fab lab in space, and we printed wafers in space, and we used zero water because we used the cold of space to cool that facility down. So if we really care about resources, if we really care about climate change, if we really care about making an impact, we have to start thinking about this kind of comparisons. We need to have these discussions with the industry, which is what we're currently having. And so my message to you is I've never planned to work for NASA. It just happened that I ended there. And so if I could do it, you can do it. Now, space is hard. I don't want to diminish I don't want to diminish the seriousity of it. And space exploration will be even harder. But I hope that you're motivated and that you can find your own call in this, because we really need the next generation to think high. So, Privește cerul. Thank you.
Thank you very much.
Thank you, Philip.
That was very inspiring.
Thank you. Yep.
So that was two very, very cool technologies that I hope soon get to life. So
well, we just need to transfer more.
So what is your time estimation?
Oh, if we have the willpower, the next decade could be transformative.
That's fantastic. So there's still a good chance. So you're still personally planning to go to space as well, I suppose.
Yeah, I hope so.
Fantastic.
I hope someone will offer me a free ride.
Well, you should have asked Mark. Maybe he takes you along next time if he has
I
a
will
place free.
definitely keep in touch with him.
Okay. Thank you so much for coming.
Sure.
It was great having you here.
Thank you so much.